Hello everyone, welcome. Thanks for joining. Thank you for being here. Get yourself ready with a notebook, a pencil, or a pen. This is math from the void. Math coming at you out of nowhere. Today we have a problem from 2008. This is from the BC exam. I presume it's a calculator question, but it could just be a BC question by hand. I see that there's a function that we're going to have to integrate. And the only way to integrate that is to use a technique called integration by parts, which is a BC technique. But other than that, everything seems completely approachable by AB, and you could solve part D with the calculator even if you're an AB. So, that being said, give yourself a moment to take a look at this problem. Give yourself some time to work it out. You can pause the video and take, like 12 minutes, especially if you're using a calculator. I mean, just 12 minutes should be plenty. Then when you're ready, you can come back and join us, because here we go. Now, looking at this chart, let's see what we got here. We have people, so we're keeping track of the number of people after T hours. So over time, we're keeping track of some people. What kind of people? We have concert tickets that went on sale at noon. Oh, nice. And they were sold out within 9 hours. It's nothing compared to the artists of today. Think about artists like Bad Bunny or Billie Eilish or Beyonce or Meg Thee Stallion or something. They sell out way fast. Taylor Swift, gosh, tickets sell out immediately. Anyways, the number of people waiting in line at a time t is modeled by a twice differentiable function. So the derivative exists and the second derivative exists. Values of L, which is the number of people in line, are available at various times. So someone just went out there and said, okay, at noon, how many people are in line? At 1 p.m., how many people are in line, etc. Okay, let's look at part A. Use the data in the table to estimate the rate at which the number of people waiting in line was changing at 5:30, at 5.5. Well, we don't have information about 5.5, but we have sort of the symmetric information on both sides of 5.5. So we can take the slope, the average slope, and that's our best approximation for the slope at 5.5, because they're asking about the rate, which basically means estimate L prime of 5.5. Okay, so we can say L prime of 5.5 is approximately L of 7 minus L of 4 over 7 minus 4. And so you just subtract the values, 150 minus 126 over 7 minus 4. That turns into 24 over 3. So we have an average change in the number of people in line is about 8. So we'll say about 8 people per hour. That means that the line is getting longer by 8 people per hour at that moment. And we don't know if it's true exactly at that moment. It's just an estimate based on what we had. So that's the computations leading to the answer. And indicate units of measure. That means if you don't include the units, they're probably going to take points off. You probably are awarded points based on including the units. Okay, part B. Use a trapezoidal sum. All right, we know that method for approximating integrals with 3 subintervals. Okay, there's a lot more than 3 subintervals here, but we'll see. To estimate the average number. So this is just an average value problem. Average number of people waiting in line. Oh, and this is important too. During the first 4 hours, it's hugely important, because during the first 4 hours, we do have 3 subintervals. Okay, so remember that the average value formula is 1 over b minus a times the integral from a to b. In this case, instead of x, we're going to use t for time, and instead of f, we're using L for the number of people, but it's the same idea. It's easy to miss the average number of people as the request. It's easy to just see the trapezoidal sum and think, oh, integral, I got this. And you do got this, and it is an integral, but there's more to it. So we're going to have, if I sort of put this over here, we're going to have 1 over 4 times the integral from 0 to 4. That's sort of our goal here. Now this is the thing that we have to approximate with some trapezoids. So let's break that down. It's going to be the trapezoid formula, 1/2 base 1 plus base 2. So take the values for the first interval from 0 to 1, 120 plus 156, and then the quote-unquote height is the span of time, so that's just 1. And then we move on to the next trapezoid. This is going to be 156 plus 176. The height of this trapezoid is 2 because it's over the span of 2 hours. And then the next trapezoid is going to be 1/2 176 plus 126 over the span of 1 hour. Okay, so I mean, there's some tricks that you can do in here. I guess the 2 and the 1/2 there kind of cancel each other out. That's sort of nice, so let's start there. 332 plus half of this plus half of that, that's going to be 88 plus 63, so 151. And then this is half of 120, that's 60, plus 78 is 138. So let's add all that stuff together, then divide by 4. Oops. This is going to give us, let's see, 470 right on the dot, plus 151, so we have 621 over 4, and this equals 155.25. Now, if you're using a calculator, it should be very, very easy. This is the approximate average number of people per hour. This is just an average. Of course, we can't have a quarter of a person. Okay, part C says, what is the fewest number of times, interesting, where the derivative L prime must equal 0? Okay. First of all, because L is twice differentiable, well, just from the fact that it's differentiable once, we know that its derivative is satisfied by the mean value theorem. We know that it satisfies mean value theorem. L satisfies MVT. That means that L prime equals the average slope at any interval. We're going to use that fact. We're going to find spots where the average slope is positive and where the average slope is negative, and that will tell us that the derivative had to go from positive to negative at some point. So let's look from 0 to 3. See how it's going up the whole time? We can say that L prime of t is positive on the interval from 0 to 3. Then we can say that L prime of t is negative. Oh, sorry. We have to say for some t. For some t on 0 to 3. And then we know it's negative for some t. And what I'm going to do is I'm going to copy and paste this because we have several intervals where this happens. Let's duplicate that. Bam! Power technology. This is going to be on 3 to 4. Let's see. I think it goes up from, it goes down from 3 to 4 on average. And then it goes up from 4 to 7. And then it goes down from 7 to 9. So that's the intervals. Those are the intervals we're going to use. We know that L prime of t is greater than 0, again, for some time, 4 to 7. And then we know that L prime of t is negative for some t on 7 to 9. Now, because L prime is continuous, we know that the IVT also applies. The IVT applies to L prime. What does that mean? That means that if we know the derivative is positive at some point and then it's negative at some point, we know that it has to pass through 0 for some, let's call it t1, on the interval from 0 to 4. And then since it switches from negative to positive, we know that L prime is equal to 0 for some t. Let's call it for some t2, which is after t1. And that's going to be on the interval from 3 to 7. And then lastly, we know that L prime is again going to pass through 0 because it goes from positive to negative for some t3, We know for sure that it does this. It could possibly cross through 0 multiple times, more than we know here, but this is all the information we have, somewhere from 4 to 9. So at least 3 times. And by times, I literally mean t values. That L prime equals 0. Okay, very highly conceptual question. We didn't even have to actually calculate the slopes. We just have to see that the average takes us higher, and then this interval, the average takes us lower. So you do have to be a little clever on where you're tracking these. But as soon as you start seeing it going up, and then it goes down, and then it goes up, you know that a change happened at some point, basically. Okay, part D, this is where I think you would just use a calculator. It says the rate is modeled by this. That's the rate. We want to find out how many tickets were sold. So if we want to add up the rates, that's the same thing as an integral. And like I mentioned, you can use a calculator for this. You're going to get points just for setting up the proper integral. And you can get whatever you get. If you were to do this by hand with a Calc BC techniques, it would be something like, let's see, 550 times the integral of t e to the negative t over 2. You would have to do this by parts, yeah. You would absolutely have to do this by parts. So this would be 550 times, do some quick math here. It's going to be negative 1/2 t e to the negative t over 2 minus, let's see, the integral of just e to the negative t over 2. So that's going to be plus, well, technically it's minus, I guess I'll write it like this. But since that antiderivative is negative, it's going to turn it into a positive. Oh, whoops, and it's not negative 1/2, it's negative 2. My bad, buddies. Sorry, everybody. There we go. So this should be negative 1100 t over e to the t over 2, kind of crazy, plus e, I guess plus 550. No, it's still 1100 over e to the t over 2. So we would just factor the negative 1100 out over e to the t over 2, and that would just be equal to t plus 1. So all of this from 0 to 3, if you plug in a 3, you basically just get negative 4400 over the square root of e cubed. Interesting. Minus, what do you get when you plug in 0? You just get negative 1100, so I guess it's just plus 1100. Okay, if I had to guess, this is like near 1000, because let's see, e squared is like approximately 7.34 or something, and then if I multiply that by e again, I mean it's 2.718. So yeah, we'll just use 2.72, I guess. When you're approximating at this point, it doesn't really matter how precise you get. Okay, let's go. 6 and 28 is 34, so that's a 3, 17, 25, and 21 makes 46. 4 makes 53, and 6 makes 59. So, I don't know, like 19.96. Oh, and then we got to take the square root of that. That's fun. So this is like approximately 4.5. So this is really just like negative 4400 over 4.5, which is, is that right? Yeah, seems about right. Seems a little weird, to be honest, though, because then that would take us to like just like almost 900. I don't know, plus 1100. Yeah, I'm guessing that's just going to take it down to like I don't know, like 970-ish. I have a feeling this integration is a little bit off, but that would be my guess. I mean, the more exact answer would be this. And then if I really wanted to, be careful about this, I would probably Oh, I think it's because there's another 2 there. Yeah, it could be that I missed a factor of 2 somewhere, basically. Because I think this should be like 2200 minus this, which should be a little bit less than 1,000 is basically my guess. Okay. Anyways, you really only get like 1 point for the final answer, so I'd be comfortable submitting that. Now, why is this question tricky? This question is tricky because you have to know how to use the chart. In these problems, you need to know how are you using these table of values. And a lot of times you have to estimate things because tables of values are not smooth. They're just discrete points in time. They're just snapshots in time. Another main pitfall, part B, make sure you're reading the question fully. It says estimate the average value of people, the average number of people, not just to find the integral. So if you just found the integral and then didn't divide by 4, which is a very easy thing to do, like computationally, you're going to miss a point just because you didn't divide by 4. That's kind of bad. Additionally, when we estimate rates, we're just taking the average slope, and that's kind of the best we can do because we don't have precise information. So those kinds of things you're going to have to be comfortable with making approximations and using estimates, but using logic still, like in part C. We know that it was going up and then it was going down. At some point it had to hit 0, right? If it was going down and then it's going up, at some point it has to hit 0. And if it's going up and then it's going down again later, at some point it has to hit 0 because of the differentiability of the function. So a couple of things where you need to be careful on how you're using the table and interpreting the question. Yeah. Anyways, that's enough blab out of me. Thanks for joining, and I'll catch you guys next time in the void.